My name is Chip Cameron, and I'm going to be your facilitator tonight. And in a couple minutes, I'll go through some meeting process issues so that you know what to expect from tonight's meeting. And this is the Nuclear Regulatory Commission's technical meeting with Southern California Edison, who we all know is the licensee for the San Onofre generating station. And the subject of the technical meeting is the licensee's response to the NRC's confirmatory action letter on the steam generator tubes in Unit 2 of the facility. This is an NRC Category 1 meeting. That's the parlance that's used, as opposed to the last meeting that we did several weeks ago, which was a Category 3 meeting. Now, a Category 1 meeting is a meeting between the NRC staff and the licensee staff to discuss potential resolution of safety issues at a particular facility. And in tonight's case, it's the confirmatory action letter on the steam generator tubes at Unit 2. For a Cat 1 meeting, most of the meeting is devoted to a discussion of the technical issues between the NRC staff and the licensee staff. However, all of these Cat 1 meetings are open to public observation, and also will open the latter part of tonight's meeting after the technical discussion. We'll open that up to all of you to answer questions, to hear your perspectives on the issues. Now, just a couple of ground rules, and I'll go over this again when we get to the discussion part of the meeting, but we won't take any questions or comments during the technical discussion between the NRC staff and the Southern California Edison staff. When we do get to public discussion part of the meeting, I'm going to come out into the audience, and I will make sure that I equitably go to every part of the audience. If you have a question or something to say, just raise your hand and I'll come over with the microphone for you. If you want to come out in the aisle, if that's comfortable for you to do that, then please do that. We've created some aisles in the middle of these seating blocks to make that easier. And I would just ask you to introduce yourself and ask everybody to give their full attention to whomever has the microphone at the moment, and listen to what they're saying. We have a lot of people here tonight, and thankfully we have room for everybody who came out. But I would ask you to follow a 3-minute guideline in your comments or questions so that we can make sure that we get to everybody tonight. And I know there's a lot of issues of concern around the San Onofre facility, just like there is at any other nuclear facility. But we really want to focus on the topic that these gentlemen are going to be discussing tonight, which is the confirmatory action letter and the steam generator tubes. We do have what we call feedback forms out at the desk in front, and these are comment forms for people to give us their evaluation of the meeting if they want to. Things we could improve on, things that were done well. But in addition to that evaluation, if you want to use it to pose a question to the NRC staff on things like seismic issues, emergency planning, or any of the issues that we won't be discussing tonight, please use those forms to do that. And as always, let's give courtesy to everybody who's talking. There's always a difference of opinion on these issues, so let's just try to respect the person who's giving that opinion. And in the courtesy, department. It is fine to have signs in the room, okay? But we have to ask you to display them in the back of the room so that they don't block anybody's view or interfere with anybody who's watching the meeting. So I would ask you to observe that. In terms of the agenda for the meeting, we're going to have some opening remarks tonight by Ryan Lance from the NRC staff. And then we're going to go to Mr. Tom Palmisano, who's right here, from Southern California Edison, and he's going to do a presentation on Edison's efforts to identify the causes of the steam generator problem, steam generator tube problem, and also what they're going to do to try to address those issues. Then we're going to go back, remarks, NRC staff. We'll take a short break of 15 minutes, and then we're going to come back and we'll go to all of you for questions. It's not clear right at the moment how long the technical discussion will be, but we'll try to provide extra time at the end of the meeting if we can, so that we can make sure that we can go out to you. And let me ask the NRC staff to introduce themselves, and then we'll have Pete Dietrich and his colleagues introduce themselves. And I just want to point out some other NRC staff that are here. Ryan?
Hi, Chip. Thank you. This is the first microphone test. I'm Ryan Lance, as Chip said. I'm a branch chief with responsibility of regulation of San Onofre.
Hi, my name is Art Howell, and I'm the just been directed to be the leader of the newly formed organization that has oversight of San Onofre, and I'll be talking about that a little bit more in a few minutes.
Hi, I'm Greg Werner out of Region 4, branch chief. I'm actually now the inspection and assessment lead for the inspection activities going forward for Song steam generators.
My name is Doug Broadus, and I'm the branch chief in headquarters with responsibility over the licensing and technical evaluation activities associated with San Onofre.
Great. And Pete?
Pete Dietrich, the Senior Vice President and Chief Nuclear Officer from Southern California Edison, and I have two of my colleagues here with me tonight. I'll let Tom introduce himself first.
And I am Tom Palmisano. I'm the Vice President of Engineering, Projects, and Site Support for Southern California Edison, and I led the technical work that we'll be summarizing tonight in our presentation.
Doug Bowder, Site Vice President and Station Manager for San Onofre.
Thank you all. I know it's going to be a very interesting and informative discussion. And this is sort of a in-joke for all of us who were at the last meeting, is that if you do go to the bathroom tonight, you'll be able to get back in the meeting. So with that, I'm turning it over to Ryan. Go ahead, Ryan.
All right. Thank you, Chip. Well, good evening again. I'll start tonight's meeting by saying in advance I look forward to a very productive discussion this evening with Southern California Edison. Mr. Dietrich, a little bit of history. 10 months ago, pretty much today, Unit 3 was operating at 100% power. In its first operating cycle with the new Mitsubishi Heavy Industries steam generators. They had been in operation for just about a year. Your operators responded to some plant alarms, diagnosed the steam generator tube leak, and safely shut down the plant. Unit 2 was already shut down. They were in their first scheduled refueling outage after having replaced their steam generators and been in operation for about 2 years. Since then, you've conducted extensive work with lots of help from folks outside your organization to figure out several things. Why the leak occurred in Unit 3, why 8 steam generator tubes in Unit 3 failed to maintain structural integrity requirements, and finally, why you believe right now that it's safe to restart Unit 2. The amount and type of tube wear in all 4 of the steam generators at San Onofre is a significant concern to the Nuclear Regulatory Commission and to many others. So we're looking forward to hearing about your work to date and specifically why you think Unit 2 is safe to restart. And with that, Mr. Dietrich, I'd like to turn the floor over to you.
Okay, thank you very much. Chip, I think I need either the clicker or one more slide.
Dave, are you ready? Okay. Here you are, Pete.
Thank you. I'll let you- Thank you. As Ryan mentioned, we are here tonight to present our Unit 2 confirmatory action letter response and look forward to the discussion tonight. Let's go on to the next slide, please. You know, we take the operation of San Onofre Nuclear Generating Station very seriously and take our commitment to protect the health and safety of the public as well as our employees with utmost seriousness. We dedicated ourselves throughout the efforts of the last 8 months of analysis to convincing ourselves first that it is safe to operate Unit 2. We're pleased to be here tonight with the NRC and the public to present that 8 months of hard work. And just to reiterate, by our submittal of the confirmatory action letter response, Southern California Edison is satisfied that it is safe to operate Unit 2. That has been a very big decision for the company, and we treated that decision as such with challenge and diverse thought. Although we relied heavily on the experience and conclusions of our experts, the final decision to submit the confirmatory action letter was clearly that of Southern California Edison, and we take full responsibility and accountability for that decision. Let's go on to the next slide. We've emphasized throughout that there is no timeline on safety. Tonight, we had desire to present over 8 months of hard work in a few hours in a manner that people can understand. But we also recognize that this will require additional questions and additional work and additional interface actions and discussion. And we are fully prepared to engage in the additional actions and discussions that we need to educate others, specifically the Nuclear Regulatory Commission, in your decision about whether it is safe to operate Unit 2. We do feel that there is substantial conservatism and safety margin in our confirmatory action letter response. And we look forward to that discussion tonight and beginning to discuss that with you. Let me now turn the discussion over to Tom Palmisano. Thank you. Tom?
Okay. Thank you, Pete. We have the mic on? Very good. Good evening. As earlier said, I'm Tom Palmisano, the Vice President of Engineering, Projects, and Site Support, and I will be presenting a summary of our confirmatory action letter response that we submitted in early October. As part of the confirmatory action letter, we committed to understanding the cause of the tube-to-tube wear which occurred in Unit 3 and implementing actions that would mitigate that cause prior to restart of Unit 2. We have submitted that material, and over the next several hours I will summarize that material for the NRC. We're looking forward to your questions. So we appreciate this opportunity, and as Pete has said, we've been looking forward to making this presentation.
Excuse me, Tom, involving questions. Can we ask you questions as we go along? Or
I'm fine if you ask questions as we go along.
Okay.
Certainly. Thank you. And if that helps our understanding, I would appreciate that. What I'm going to do tonight is kind of give an overview of the background, just a brief synopsis of the history of the replacement steam generators, picking up on what Mr. Lance said, just summarize the tube leak that occurred. I am going to talk a bit for the benefit of the public about just an overview of the steam generator construction. I think that's useful, so as I talk in more detail about tube-to-tube wear and vibration, it puts it in context for everybody in the room. And then we'll get into the specific cause of the tube-to-tube wear and the corrective actions we have developed and implemented and proposed to the NRC. With that, just a brief history of the replacement steam generators has been noted. They were fabricated by Mitsubishi Heavy Industries. The contract was awarded in September of 2004. The installation actually started for Unit 2 in the fall of 2009, and the Unit 2 then resumed service in early 2010, and Unit 3 replacement started in the fall of 2010 and returned to service early in 2011. The design and fabrication was done largely in 2005 through the 2008 timeframe, followed by shipment to the site. The replacements were done in full accordance with NRC requirements for a modification to the plant and replacement steam generators. And in fact, as you know, 2 license amendments were submitted and subsequently approved by the NRC related to the steam generator replacement. Now, the Unit 3 tube leak, as you mentioned, on January 31st, 2012, Unit 2 was already in a planned refueling outage for about 3 weeks at that point in time. Unit 3 was running at full power. A small primary to secondary leak occurred, leaking radioactive water from the primary into the secondary. The installed plant monitors responded properly, very quickly, and identified a slight increase in radiation levels on the secondary side. The operators recognized it, diagnosed it, and responded very effectively in accordance with our procedures, and ramped the unit down, took it offline, and proceeded to shut down and cool down the reactor and the primary coolant system. The leak occurred after 11 months of full power operation following installation of the new steam generators. Certainly a disappointment to Southern California Edison and to our customers. Inspections that occurred then in February after we established safe conditions in Unit 3 identified a unique and heretofore unseen tube-to-tube wear phenomena in this style of steam generator. Has not been seen before in the domestic industry in the U.S. nor internationally, this tube-to-tube wear. And I'm going to talk quite a bit about that tonight. And I'm going to put that in perspective with respect to our actions on both Unit 2 and 3 in a minute. Now, as Pete has emphasized, our commitment to safety and ensuring we understand and mitigate the cause well beyond a commitment under a corrective action letter, our commitment to ourselves and our stakeholders and our public. Okay? We step back and we recognize the significance of the Unit 3 condition. A primary to secondary leak in brand new steam generators is significant by itself, but as we saw the data indicating the unique tube-to-tube wear, it clearly was an indication that something that had not been seen before in operating steam generators had occurred. We also stepped back. Unit 2 was completing its refueling outage by the end of February, and Unit 2 had in fact met all the requirements, including steam generator integrity requirements based on a full inspection, and could have legitimately been started up under the license. We elected not to start up Unit 2 until we better understood the issue in Unit 3 and the susceptibility of Unit 2. We felt it was a prudent, safe, and conservative decision not to rush to restart Unit 2. So we delayed restart of Unit 2 as a prudent, conservative action. Public health and safety is the first and foremost issue. And in developing our corrective action, we have used the best worldwide expertise. Pete alluded to this, but I've been in the commercial industry for over 30 years now and involved in engineering and operations, and we have assembled a team of not just Mitsubishi and Southern California Edison, but every other steam generator manufacturer and designer in the U.S. and internationally with extensive experience, a significant team of experts, including academics with some specific knowledge of vibration and thermal hydraulics. Probably the best team I've ever seen put together, and we have spent the last 8 months really understanding this and making sure we know what the issue is, know that the corrective actions for Unit 2 will be effective. We had over 200 engineering people when we collect the people from all these vendors, all these consultants, and our own people and our utility peers, and another 600 technicians assisting us during this effort. And the bottom line is, as we made our CAL submittal here in early October, and as we make our presentation tonight, we have ensured that there is significant safety margin in the Unit 2 analysis and the Unit 2 corrective actions prior to restart of Unit 2 to ensure we will maintain tube integrity. I want to just outline the methodology. This is one of the items that we discussed as we established the meeting requirements for tonight. So at a high level, I've already mentioned we engaged world-class experts. We did not just rely on our own expertise, which is substantial, nor did we rely just on Mitsubishi's expertise.
Excuse me, Tom. May I
Yes.
ask a question? You had indicated that this tube-to-tube wear had not been seen anywhere in the world, either in the United States or in other countries. Yet there is experimental research test data that indicates that the cause of the tube-to-tube wear could in fact happen. And so my question is, do you plan to address that tonight? Were your staff or the vendor staff aware of that back at the time that the steam generators were being designed?
I'll address it briefly tonight, and I think as we complete root cause work, we'll get into that in more detail over the subsequent several weeks and months. What I'm referring to is in operating steam generators, this phenomena had not been seen nor occurred. Okay? What you're alluding to, Mr. Howell, is and to jump ahead in the presentation, fluid elastic instability is the technical term for the cause, which causes a high amplitude or high displacement vibration of the tubes, which caused them to contact each other. That dated back to about the 70s, not in steam generators, but I think in condensers initially.
Actually, there was some work done in the early 2002 timeframe in Canada.
Well, I'm going to run you forward through the timeline. So the phenomenon was recognized in the 70s as a theoretical phenomenon, demonstrated over the years. There's been research in the last 10 to 15 years that has demonstrated in some test facilities. But again, it had not been seen in operating steam generators. And up until the point of San Onofre Unit 3, the information had shown that if you adequately design against normal vibration and adequately design against what is called out-of-plane vibration, you will have substantial margin to this in-plane vibration and fluid elastic instability. So that's where the research had taken us. As far as 2005, 2006, we are in the process of completing our root cause work, so I'll defer more discussion on that to a later point in time.
Okay, thank you.
Back to methodology. World-class team of experts, but very systematically then, we start with what happened in Unit 3. Why did the tube leak, which led us to the tube wear indications and led us to the fact that tubes were contacting each other. So they're vibrating excessively, well beyond what they were designed to do. So then what's the cause of excessive vibration? We identified that cause, we validated that cause with some of the research you're talking about, with some of the experts we brought in who actually authored and did some of that research. And then we determined our corrective actions, understanding what causes it, and it's particularly thermal hydraulics, and I'll talk more about that tonight, as well as lack of damping due to the support structure. So we identify the cause, we identify the contributors to the cause, then we develop the corrective actions to prevent that in Unit 2. And we validated the cause and corrective actions again with the experts. We didn't just not rely on our own judgment on this, and we've ensured substantial safety margin exists in the actions we have proposed in the confirmatory action letter response. Just to summarize some of the expertise, Mitsubishi Heavy Industries has designed and built steam generators for a number of years. Arriva, a worldwide firm, designs and builds steam generators. Westinghouse, worldwide firm, designs and builds steam generators. B&W Canada designs and builds steam generators. Mitsubishi agreed early on to bring 3 of their competitors in to scrub their work, their design work, their analysis work, and their conclusions to make sure we didn't have a mindset, we didn't just rely on their expertise or our expertise. This has been unparalleled cooperation. I know you and your work as a regulator would recognize the level of cooperation that these companies have exhibited in understanding and solving this problem. We also mobilized MPR Associates. This is a firm who specializes in problem solving of technical issues, nuclear and non-nuclear. Work in many different industries, and their expertise is problem solving, a systematic approach. They help us avoid a mindset, if you will, and we've used them both for technical reviews, and Pete has used them as an oversight role to ensure that we're doing our job effectively and not getting focused in on an easy answer. As well, we have EPRI, which is the Electric Power Research Institute. This is the research arm of the electric utility industry, not just nuclear, strong nuclear expertise, 50 years, almost 50 years of steam generator experience. And they develop and maintain the steam generator program that we are all committed to in this country. And then likewise, we have other industry personnel from peer utilities, recognized academics and specialized consultants. This gets to some of the people who wrote the book and did the research in the last 15 years on fluid elastic instability. So now I want to shift and kind of give an overview of steam generators. Okay, I guess I want to make sure as we get into the more technical terms, we're all baselined on this. I'm going to attempt to use the pointer. The staff's done a great job. I'll try not to hit anybody in the head. It's a little green dot. It's a little difficult to see, but we'll do our best here to be able to point at either screen and show you some of the aspects of the steam generators I'm talking about. First, a pressurizer water reactor layout. I just want to talk about the steam generator itself, its function. In the center of the containment building, this is the building that looks like a dome. Okay? You've got the reactor itself shown there in yellow with the red fluid being pumped through it. That's where the nuclear fuel is. The water circulates around the fuel and removes the heat from the fission process in the fuel. That is a self-contained primary system, referred to as the reactor coolant system or the primary coolant system. That water flows inside the tubes in the steam generator. In a couple minutes, I'm going to show you some schematics and then some pictures to put that in perspective, but that water flows inside the tubes. And the heat from that hot water out of the reactor is transferred across the tubes to the secondary side where we boil water to make steam. So on the secondary side of the steam generator, shown in blue is water being pumped in at the bottom, boiled to steam, steam comes out and turns the turbine and then the generator. If this were a coal plant, if this were a gas-fired boiler, that part of the process is the same. We heat water, we make steam, we turn a turbine generator. Now, with the steam generator specifically, a couple key functions. First of all, the nuclear safety function. The fuel is inside fuel rods inside the reactor. The fuel rods are designed to keep all the fuel and all the high-level radioactive waste products in the rods. That's the first barrier, is the fuel rods. We call it the fuel clad. The second barrier, if there were a leak in the clad, is the reactor coolant system itself that you see in the yellow and in the red going around in our little animation there. And that includes the steam generator tubes. So the steam generator tubes have a very important safety function. They're a boundary, they're the second barrier, if you will, to fission product release to the environment in the event of an accident. And the third classic barrier is the containment structure itself. Okay, in the event the second barrier, the first barrier and second barrier were to fail and we have radioactivity in the containment building, the structure itself is designed as the third boundary or barrier. So the tubes have an important safety function to contain radioactive material. They also have an important function. They transfer heat for normal heat transfer when the plant's operating normally, to boil the water to steam to turn the turbine. And they're also how we remove heat from the reactor after it's shut down through the steam generator tubes to the secondary side. So safety function to contain the radioactivity, and a heat transfer function both for normal purposes, shutdown purposes as well. The primary to secondary leak that occurred in Unit 3 and the significance of the tube-to-tube wear in Unit 3 is that's a breach in that second barrier. When a steam generator tube leaks or doesn't maintain integrity, that's a breach in the second barrier that is important from a safety standpoint. That was at the heart of our decision not to restart Unit 2 until we understood the phenomena, our commitment to safety and our commitment to our public. A little more on steam generators. This is a good schematic cutaway of an actual steam generator. We've effectively cut it in half. The hot water out of that reactor flows in at the bottom. It's called the hot leg. And by the way, out in the hallway, there's another schematic picture of this as well as some models of tubes and things for you to look at. The hot water flows up. We refer to these as a U-tube steam generator. The hot water comes in the bottom, flows up. The tube is literally shaped in a U, and you'll see a picture. And the water from the reactor then, after the heat is transferred to the secondary, comes out the cold leg and is pumped back in the reactor. So with tube integrity maintained and no leaks, all that water stays contained and just circulates through the reactor and the steam generators. On the secondary side, not as easy to see, we pump that feed water, we call it feed water, into the secondary side of the steam generator. It comes down on the outside and flows up through the tubes. And as it flows up, it starts at the bottom as water, and as it flows up, the heat is transferred and the water boils and steam exits the top. So later when we talk about fluid velocities and steam quality and things, that's in the middle of the tube bundle, particularly the upper part of the bundle where the water has been boiled to steam and the steam's about to go through the very top. In the top, I'm not going to spend any time on it. That is steam drying equipment to strip any remaining moisture out of the steam before it goes to the turbine. So I want to show you what steam generator tubes look like. These are large components. These are over 60 feet tall, probably weigh 600 tons each. You're looking at something about 15 foot in diameter. That's the opening of the top of the steam generator. This is a picture during actual fabrication where Mitsubishi is about to start inserting tubes. These are long, thin, very strong tubes. It's a material called alloy 690, which is used predominantly in all the replacement steam generators in the industry. It is very corrosion resistant. It's a very good choice for steam generators. You're looking at the top of what's called a tube support plate, and you're seeing actually a set of tubes about to be inserted. That's a column of tubes. I'm going to show you a close-up picture in a minute. The key thing in a column, the tubes adjacent to each other in a column are physically separated only by a design gap. There's no physical separator between the tubes in a column. And this is one of the things that allowed the tubes to contact each other. A little better close-up. Again, you see some tubes being inserted. You see a column partly built out. You see them inserting in the next tube. You see a number of columns already completed here. And you see the ends of anti-vibration bars. There are physical bars, and I'll show you some more graphics in a minute that illustrate this a little better, that separate columns from each other in adjacent rows. So tubes are organized in rows and vertically in columns. Think of them that way. The anti-vibration bars dampen any tube movement and physically separate tubes in adjacent rows, and that is their function. This is just a picture. The tube bundle's been completed. This is just a close-up of the very top, and I'm going to zoom in and show you a little detail in that red square. So looking at some detail in the square, you're seeing what is the top of the tubes. These are the top of the tubes here. You're seeing the end of the anti-vibration bars, and you can see how they go down between each column to separate the rows. You're seeing the very end. These are V-shaped. And you're seeing something called a retaining bar, this heavy bar here, and a retainer bar underneath. We did find a wear phenomena that was unexpected. It only affected 94 tubes in each of the 4 steam generators, but it is something we found, we discussed in the confirmatory action letter response. So I'm going to briefly status that tonight and then get on to the tube-to-tube wear. Okay, back to our cutaway of the steam generator. We're going to do a little zooming in here with some of our computer-aided design tools. We're going to zoom in on the upper part. Where the wear has occurred that is of most concern is the tube-to-tube wear. This is the unusual wear not seen before in operating steam generators that in 11 months of operation caused the through wall leak in Unit 3. We're going to be focusing tonight mainly on this upper part of the tube bundle we'll call the U-bend region. This would be, say, the hot leg side. This is the cold leg side. The green things are tubes. There are 9,727 tubes in each of the steam generators. 2 steam generators in each unit. So I'm going to just round that off to about 10,000 per steam generator. But in this tool here, we're able to, just show you a segment so we can talk about the structure. You see here these bars coming down. You'll see a close-up. These are the anti-vibration bars that I've referred to and showed you in a picture. Zoom in a little more. Okay, so now we get a pretty good look. The green tubes, and you see the anti-vibration bars coming down. You see, where we've exposed this tube column, you see how they run down the entire length of the column, and you can see the heads or the tops of the other anti-vibration bars between adjacent columns. I've also annotated the slide to show in-plane and out-of-plane direction, and this is important. The real phenomenon in Unit 3 with this tube-to-tube wear, this excessive vibration, is a problem with in-plane motion. It has not been seen before, and this is what causes excessive movement of the tube, which allowed a tube to vibrate and contact a tube above and below it, and cause the amount of wear we saw and ultimately the leak. In the out-of-plane direction, tubes would tend to vibrate sideways, and they are restrained by the anti-vibration bars. I should say, in any steam generator, we know there is normal vibration. There's water flow and steam flow. There's turbulent flow. These tubes vibrate normally. You account for that in the design. You account for that in the material selection. And steam generators have run 20, 30, and 40 years with normal vibration and normal wear.
Excuse me, Tom, you talked just a minute about the function of the anti-vibration bars. Can you talk a little bit about the design and the design philosophy about the anti-vibration bars?
Could you clarify design and design philosophy?
Sure. It's my understanding that these anti-vibration bars were designed so that they would have zero gap and zero contact force in between the rows of tubes so that you would prevent tube to anti-vibration bar dings and dents due to wear of the anti-vibration bars with the tubes. And that represented a change from the previous design philosophy that your vendor had used in making steam generators.
I will give you an answer about the design of the anti-vibration bars. As far as MHI's previous design philosophy and current design philosophy, that's not something I'm prepared to speak to, and we can answer that at a later point in time with MHI. So rather than me speak on their behalf, their root cause work is ongoing as well. With the anti-vibration bars, what Mr. Howell's referring to, these anti-vibration bars, it's a fairly similar design used by other steam generator manufacturers. Again, most of the vibration that is experienced in a steam generator is normal random vibration, and they're designed so when the steam generator is hot and operating, the vibration bars have a zero gap. They just contact the tubes without significant force, because you want the tube to be able to experience some vibration without excessive force wearing at it. They are designed to limit the out-of-plane displacement of the tubes. And again, this is a typical design that several of the vendors use in these larger U-tube steam generators, and it's evolved over the years.
So I just wanted to make clear they were designed to prevent out-of-plane displacement.
They're designed to prevent out-of-plane displacement. They also provide some damping to in-plane vibration, and I'll talk about that in terms of fluid film damping and just friction damping when they're in contact with the tube. But again, industry experience up until the San Onofre Unit 3 issue was that if you have adequate margin to out-of-plane vibration by your analysis, by your thermal hydraulics and support system, you had more than enough margin to in-plane vibration. One of the things that has occurred here is there was less margin recognized in-plane vibration, and you'll hear me later say the support system was not effective in Unit 3 in restraining the in-plane vibration.
But that in-plane vibration that's prevented is based on operating history, right? Not on analysis or testing? Or...
Based on operating history. The analysis typically looks at normal random vibration and out-of-plane vibration. Okay, so that's an overview of the steam generator construction, and that sets the stage really to start talking about the inspection results we found, the cause of the tube-to-tube wear, and the corrective actions. So I'm going to take Unit 2 first, and then I'm going to take us into Unit 3. Unit 2 is already in a planned refueling outage. So at the end of the first cycle with new steam generators, and let me give you some background. When new steam generators are built, designed, and fabricated, before they are installed, you do 100% inspection of all the tubes after fabrication, before installation. So you have what's called a pre-service inspection or pre-service baseline. So you absolutely know the condition of the tubes. And after the first full cycle of operation, you repeat a 100% inspection. And that's your first comparison of how the steam generators and tubes performed from your pre-service inspection to your first in-service cycle. Then typically your program has you go forward with periodic inspections of samples of tubes if your results have been acceptable. That's how the program works. So in Unit 2, we had entered Unit 2 on January 9th, 2012, so we had done a full scope inspection. We did 100% of all the tubes, all nominally 10,000 tubes in each steam generator with what's called an eddy current bobbin coil. This is a sophisticated device that is run up the entire length of a tube. To give you some perspective, those tubes at the very top of the bundle, the outer tubes, are 76 feet long, inlet to outlet, okay? So in all of those 9727 or roughly 10,000 tubes, we run a probe up that through an electrical signal assesses the tube wall, looks for any indications of dents, dings, wear marks, etc. Okay? It's been used for many years. This technology is proven and it has been refined through the EPRI, Electric Power Research Institute program. Then we do...
Tom, can you talk about the sensitivity of that probe device? I think you're going to talk about a different type of probe here in a minute.
I don't have the sensitivity specs with me, Mr. Lance.
Or like how small of a indication or something that could detect reliably.
Rather than quote something off the top of my head, I'll be glad to answer that either after the break or later. I just don't have that number on top of my head. It is a fairly sensitive examination. What you're referring to is the next bullet, the eddy current rotating coil exam. This is a different type of probe that is slower and is used for a sample of the tubes or for certain areas. If we see an indication with the eddy current bobbin coil probe, we go through with a rotating probe which has different sensors on it, which is a greater sensitivity and allows us to characterize something we might see on the bobbin coil probe. Then we did a full U-bend exam of tubes adjacent to the retainer bars. When I talk about the results, the retainer bars in each steam generator affect 94 tubes out of the 10,000 in each steam generator. They're there largely for fabrication support. They do have a function in certain accident scenarios to restrain the tubes, but they largely have no function in normal operation. The retainer bars had a design problem and wore some wear marks on some of the tubes, not through wall. So we did a full examination of those tubes. We also then, from the secondary side, go in with cameras and do a visual inspection. All the eddy current stuff I'm talking about is done from inside the primary side of the tube. The visual inspections are done from outside the secondary to correlate what we may see on the electrical testing signals visually. And then we do special eddy current and ultrasonic exams, and especially driven once we got the data out of Unit 3 and decided not to restart Unit 2, we went back into Unit 2.
Tom, could you just take a moment and describe what that design problem was for the retainer bars?
On the retainer bars?
Yeah.
Be glad to. You're getting ahead of me, so we'll cover it now. So the retainer bars. If you remember the graphic I showed, there's a long retaining bar, and the retaining bars span the entire top of the tube bundle. There's multiple retaining bars. Underneath the retaining bars and welded to them are a series of smaller retainer bars. And half the retainer bars are about 2 foot long with a fairly thin diameter, thinner than MHI had used in the past. Those retainer bars, in the normal operating conditions at 100% power, vibrated. Just the half of them that are the longer and narrower retainer bars. They vibrated, and they wore that vibration, which was unexpected out of the retainer bars, wore against some of the tubes. Now, this is not tube vibration, it's not tube-to-tube wear, it's a retainer bar to tube issue. Wore an unacceptable depth in an operating cycle. Now, we identified that fairly easily in Unit 2, and as you're well aware, but just to state it, whenever we do a steam generator inspection, we know there's normal vibration, we know there's occasionally wear indications. When we find, and those are manageable, we manage those, we trend those, we have plugging criteria in our technical specifications. The retainer bar wear is not a normal expected vibration issue. It was clearly a design flaw, so we then preventatively plugged all the tubes affected, all 94 tubes in each of the 4 steam generators affected by the retainer bar. And the design flaw itself, MHI had used this design in the past successfully, but in the size of these steam generators, these were the largest U-tube steam generators MHI had designed and built. And in upsizing to this level, these bars were long and thin enough that they basically fluttered. And you know, that's physically what happened that caused the wear in the tube. That was not recognized by MHI. They didn't do a unique analysis for the retainer bar vibration. That was the error that was made. Does that answer your question?
I was saying, Tom, my understanding is there's 2 sizes of retainer bars.
Yes, there are.
There's a thicker one and a thinner one. So I guess I want to understand now. In the new design, did they make a retainer bar thinner than they had in the past, or
Yes.
thicker than they had in the past?
If you think of that picture of that whole bundle, when you're near the top and center of the bundle, your bend radius is much larger. You can have thicker bars. As you get to the edges of the bundle, because of the bend radius, you've got thinner bars. And in fact, for half of the retainer bars, they used thinner bars than they had previously used. And again, their mindset was that, you know, previously this had been successful. It was not an operational item in their mind, so they didn't do the vibration analysis on the thinner bars.
Okay.
So it's related to the use of the thinner bars and the length of the thinner bars. Okay, so Unit 2 steam generator inspection results. Again, the Unit 2 steam generator inspection was largely done when we got into the Unit 3 results, so we went back in. And I should mention, to give you some perspective, we have done over 170,000 tube inspections between the 2 units.